Hello, everyone, and welcome to the third part of the Strategic Learning in Wireless Communications course. This part will be about edge machine learning, or in other words, distributed machine learning. My name is Anis El-Gibli, and I will be teaching this part of the course. I will start by motivating this part of the course. We all know with the Internet of Things and Internet of Everything paradigm, a huge amount of data is generated everywhere and every second. Here I give a few examples. We have smart cities, smart healthcare, smart farms, connected vehicles, self-driving drones, and smart factories. So with the huge number of IoT devices and the huge amount of data they generate, we believe that machine learning computations need to move to the edge. Therefore, distributed machine learning is all about moving ML computations to the edge. To explain what it means and also what advantages it brings compared to centralized learning, let's first revisit centralized learning, or what we call cloud-centric learning. As we can see in this example, in centralized learning, we have a number of devices. Every one of these devices is exposed to its input data and wants to infer some kind of output or calculate an action based on an observed state. All these devices in the training phase, they need to train a global model that resides in a central entity. So every one of these devices will communicate its raw data to the cloud, and where a training algorithm is performed to compute a global model. But these devices still also need to communicate with the central entity even at the inferring phase. So every one of these devices needs to propagate its input to the central entity, and the central entity will run the global model to compute the output and send the output back to the device. And that brings the following issues. The first issue is the high latency. As I just explained, these devices, they communicate their raw data not only in the training phase, but also in the inferring phase. Therefore, for the like latency sensitive applications, this may create a significant problem. The other issue is the communication cost, and that's due to two reasons. The first reason is that every one of these devices is sending its raw data. The raw data size could be significantly large. For example, the data could be a video or image, and that will consume a lot of bandwidth. The second reason is that all these devices are competing the limited bandwidth. So therefore, as we add more and more connected devices, the available bandwidth to each device will be lower, which means like a communication bottleneck. The last but not least is the privacy issue. As we can see here, that the data leaves its origin and it's communicated all the way to the cloud. Therefore, that doesn't preserve the privacy of the data of each of these connected devices. In contrast to that, in distributed learning, as we can see, every device has a local model. It's exposed to its input data. It has a local model. Now, all these devices are training their local models collaboratively without sharing their input data. So this way of performing learning is already preserving the privacy. So the privacy is not issue here because the data doesn't leave its origin. That's the first advantage. So at high level, and we will come to the details later, at high level in distributed learning, the system will run an iterative algorithm. At every iteration, every device will perform some local computation, and then it will share some output to a global entity. That output could be the model, the local model, or the model output. It will share it with the parameter server or the central entity. The central entity will perform a global computation. It will come up with a new model, and it will share that model with all of the connected devices. Now, once the training phase is done, the inferring phase doesn't require any communication with the central entity. Every one of these connected devices can perform the action or infer the output locally here, because using the local model. So therefore, the latency can significantly be reduced, because as I just explained it, for every input you compute the decision locally, and then you just perform the local decision. So you don't need to communicate the data all the way to the central entity for the inferring phase. It will also reduce the communication cost, and we can see clearly the reason. First of all, in the inferring phase, there is no communication with the central entity, and in the training phase, all these devices are not sharing their local data. They are just sharing few parameters. It could be the model parameters itself or the model output, which in terms of the size is significantly less than the raw data. And I just explained it, it's a privacy preserving, because none of these devices is sharing its input data. And in some sense, we can also say it also minimizes the computation cost, because the computation is distributed. So every one of these connected devices is contributing to the computation process, and it's not heavily relying on one device. Now I describe a machine learning task in a nutshell, and I will focus into supervised machine learning for now. In a supervised machine learning task, we have training data that we input to a model, okay, in order to produce an output, a predicted output. And our goal is to train this model to minimize a loss function that is a function that relates, that represents some distance between the predicted output of our model and the ground truth or the actual label of the input data. Therefore, our goal is to run some optimization algorithm that minimizes this loss function between the predicted output and the actual output. And this loss function is an application dependent. For example, if our task is linear regression, then the norm 2 of the difference between the predicted and the real label could be a good function to use. If we are doing image classification, then cross entropy could be a good function to use. And for the training data, if the data size is small, then we can train this model deterministically by feeding the whole data at every iteration and keep updating the model until we converge to the optimal solution if the function is convex, or at least the local minima if the function is non-convex. However, if the data size is very large and we cannot feed it at every iteration, then we run a stochastic algorithm where at every iteration, we feed one mini batch of the data, small mini batch of the data to the model. We update the model using our optimization technique. And then we keep, at every iteration, we keep selecting a new batch randomly and feed it to the optimization algorithm and keep updating the model until converging to the final model. In the previous slide, I described how to train a model in a single machine. However, the focus in this course is to extend that to distributed learning. So where we distributed or federated learning, where we train a model in a distributed way across multiple machines. And that can be performed with the help of a parameter server, as we described it previously, and as it's shown here in the figure to the left, where every worker is communicating with the same central entity in the training phase, or using decentralized learning algorithm, where every worker is just communicating with a few nearby neighbors. And if the graph is connected, eventually every worker or an agent in that connected graph will converge to the same model. So here are a few key points we need to be aware of before we dive into distributed machine learning in details. So we need to understand the network topology. Is it parameter server based topology or decentralized topology? And also what kind of function we are dealing with. Is it convex function or non-convex? Are we training using all the data set at every iteration? So we train deterministically, or we perform stochastic training by feeding a randomly selected mini batch at every iteration? What's the structure of our optimization problem? Are we formulating unconstrained optimization problem or a constrained optimization problem? Is it the sum of separable functions, non-separable functions? What kind of algorithm we are proposing? For example, for the parameter server-based topology, if we have an unconstrained optimization problem, we usually solve that problem using either gradient descent or stochastic gradient descent when dealing with large data set. For the constrained optimization problem, we could use dual decomposition or alternating direction method of multipliers, or what is known as ADMM. For decentralized topology, we can have a decentralized version of gradient descent or stochastic gradient descent, or dual averaging, or group ADMM. All these algorithms, or some of these algorithms that we will describe later in details. Okay, before I talk about what is in this slide, okay, before I talk about what is in this slide, I would like to mention that convex optimization is a course by itself, and this course is not about optimization or convex optimization. This course is about distributed machine learning, but I will briefly remind you of key properties of convex set, convex functions, and convex problems. So I will start with a convex set. As you can see here, from this figure, this is a convex set because in any line, in any point in the line between 2 points in the set belong to the set. So if I randomly pick any 2 points, if I draw a line between these 2 points, every point in that line is still in the set. If that's satisfied for any 2 points I pick up, then this is a convex set. And this is the equation that reflects the line between the 2 points x and y. So for example, according to this definition, this set is non-convex, because if I pick these 2 points, there are some points in the line between these 2 points. There are some points that are not belong to the set. Therefore, this is not a convex set, and we call it non-convex set. So for example, this is a convex set, okay? In fact, the intersection of linear constraints is always a convex set. So if I have a convex objective function that is constrained to a set of linear constraints, the intersection of all these linear constraints form a convex set. Therefore, if the function is convex and the set is convex, then the whole optimization problem is convex. And that's what we are trying to explain here. So now we're moving from convex and non-convex set to convex and non-convex function. Okay, so for a function to be convex, first of all, the feasible set itself has to be convex, and that's necessary but not sufficient, because the function itself needs to be convex. This is a convex function, and if I want to simply define a convex function, in a convex function, every local minima is a global minima. So according to this definition, this is a convex function, but this is not a convex function, because this is a local minima, but it's not a global minima, because this has a lower objective than this one. So not every local minima is a global minima, but here every local minima, and in fact here in this specific case there is only one local minima, and it's also the global minima. So that's a convex function, and this is, if you flip that, we have a concave function. Okay, so this is like the definition of convex, concave, and non-convex function. So the convex function could be strictly convex when, like for example here, if we look into the figure to the right, so this is a strictly convex function, but this is not a strictly convex function, it's just a convex function. Therefore, from the figure we can notice what's the difference. Here there are like many points, all points in this line are global minima of the function, while here there is only one global minima of the function. If we want to mathematically explain the difference between these two, so here we can say like the value of the function at any line between 2 points has to be less than or equal a weighted sum of the value of the function at these 2 points, okay, where lambda is between 0 and 1. So when this inequality, when this is less than or equal, then this is a convex function. However, if it's strictly less than, then this is a strictly convex function. Now we come to the definition of strong convexity. We say a function is a strong convex if there exists a quadratic lower bound in the growth of the function. And since quadratic functions grow faster than the linear functions, therefore every strong convex function is a strictly convex function. And we say a differentiable function is strongly convex with parameter m that is greater than 0 if this condition or this inequality is satisfied, or an equivalent way this condition is satisfied. And if we look into this term here, what this inequality says, it says that since this term reflects the growth of the function between any 2 points x and y, what this inequality says that this growth is in the function is lower bounded by this quadratic term. This is the norm 2 or square of the difference between the 2 points. So if there is m greater than 0, such that this inequality is satisfied for every point, for any 2 points x and y in the function, then we say this function is m strongly convex. And this is an equivalent way to look at this condition. So here, function, the value of the function at y should be greater than or equal to this term that includes this quadratic term. And for a non-differentiable function to say it's a strongly convex, we have, because here, this is here for differentiable function, we can get the gradient. But for non-differentiable function, we have an alternative condition. If this condition is satisfied, then we say that this function is m strongly convex for a given, when it's satisfied for m, like a choice of m that is greater than 0, then we say this function is m strongly convex. Now, when m goes to 0, then in fact, what happens is that strong convexity approaches strict convexity. We don't say this is a strongly convex function, but we say this is a strictly convex function. And when m is equal to 0, then the growth of the function is greater than or equal to 0. That's exactly the definition of a convex function. Okay, now I describe federated learning or distributed machine learning in more details. I will start with the simple and constraint optimization problem. Assuming a system consists of n workers or n agents, everyone is exposed to its own function or loss function and its own data, and everyone wants to optimize its own loss function, but all of the workers need to agree on a global model. So this model is shared across workers. Therefore, we minimize the sum of all local functions. And a well-known method to solve this unconstrained optimization problem is what is known as aggregated gradient descent or distributed gradient descent method. In distributed gradient descent method, the parameter server will start with an initial guess of the global parameter theta. It will broadcast that parameter to all of the workers, and every worker will compute its own gradient, the gradient of its own function with respect to this theta, to this global parameter, given its own input data. And then all the workers will upload their gradient vectors to the parameter server, and the parameter server will form a system gradient, which is the aggregated gradients of all workers, and then will perform one gradient descent step. So at iteration theta k plus 1, the model is updated according to this equation, where we move in the negative direction of the aggregated gradient or the system gradient. The movement is controlled by the step size or the learning rate alpha. And why we move in the negative direction of the gradient, we all know like that the gradient vector is a directive vector that always points at the maximum increase of the function. Therefore, if we are moving in the negative direction of the gradient, we are moving in the direction where the function is decreasing. And eventually, with a small step size, eventually we will reach the optimal solution or the minimum point of the function. If the function is convex, we said this is, if the function is convex, then we are reaching the global optima. If the function is non-convex, we at least reach a local minima. So the step size or the learning rate alpha plays very important role in the convergence of the algorithm. So if we choose alpha very large, for example, we may jump to the other side of the valley. However, if we choose alpha to be very small, we keep moving towards the minima, but we will have a slow convergence. Therefore, the choice of alpha is very important in controlling the convergence speed as well as the convergence itself. As I just mentioned, if every function is convex, then the sum of these functions is convex. Therefore, gradient descent is guaranteed to converge to the optimal solution of the problem. Now we come to the stochastic version of the gradient descent algorithm, what is called the stochastic gradient descent, or mini batch stochastic gradient descent. So because sometimes the data of each worker, the data size is large, and if the worker uses the whole data to update its own gradient to compute its own gradient at every iteration, that may computationally be very expensive. Therefore, what it happens in this case, each worker will compute the stochastic gradient. So it it randomly picks one mini batch, like for example here, the mini batch zeta at iteration k is picked by worker I. So it picks randomly picks a small mini batch, and then it will compute the gradient with respect to every sample in that batch, and then will average those gradients to come up with the stochastic gradient. And that stochastic gradient will be used as unbiased estimate of the gradient of the function at iteration k. So that's the only difference compared to the deterministic case, where every worker is computing the gradient. Here, every worker is computing the stochastic gradient, and xk here replaces theta k in the previous slide. So this is the model, and this is the mini batch zeta that is picked up at iteration k by worker I. So the stochastic gradient is function not only of the model, it's function of the model and the mini batch we picked. So that's this step. Now, after every worker computes the stochastic gradient, then the rest is the same. Everyone will upload its stochastic gradient to the parameter server, and the parameter server will perform one global step, which is one stochastic gradient descent step in this case. one final thing to mention here is that uh, every worker uses a small mini batch at every iteration to compute the stochastic gradient. So using small mini batch instead of the whole data set, that can reduces the computation cost. Okay, but every worker still need to communicate with the parameter server at every iteration. Uh, so we are reducing the computation cost, but in terms of the communication cost, in fact, we may increase the communication cost because by computing the stochastic gradient, we may need more number of iterations to converge. So more number of iterations means more number of communication rounds. So one way to reduce the number of communication rounds is to use federated averaging, which uses local SGD or local stochastic gradient descent. In local SGD, there are two steps. First, the parameter server at iteration K will share a global model with all of the workers, but then every worker can perform a number of local SGD steps before sharing its updated model. So here in local SGD, the SGD step is performed at the worker side, not at the parameter side, not at the parameter server side. So every worker, after receiving the global model, it will perform tau local SGD steps to come up with a new model. Then at the second step, after all workers upload their new models to the parameter server, the parameter server will just average these models to produce the new global model, and the process repeats again and again. So therefore, the workers are not communicating with the parameter server at every iteration. They are communicating with the parameter server every tau iterations, so that can reduce the communication cost. However, one issue with what we described here, the local SGD, is that by performing a number of local SGD steps before sharing the model, so the tau, or the number of local steps, can highly affect the convergence guarantees of the algorithm, because the difference between the new model and the previous global model may grow so large, and that may lead to divergence in the algorithm. So therefore, elastic averaging was proposed, and in elastic averaging, it follows the same steps of the local SGD. The only difference is that after computing, after performing a number of local SGD steps and coming up with the new model, the worker doesn't share the new model. It shares a linear combination between the new model and the previous global model. And the reason behind doing so is that to pull the new model back towards the previous one, so the difference doesn't grow so large. So here, if you look into this linear combination, so at the extreme case, when alpha is equal to 0, then we don't care about the previous model. So we just take the updated model and upload it to the parameter server. Therefore, this what we are doing is exactly local SGD. However, when alpha is greater than 0, then we are taking a linear combination between the new model and the previous one. So we still consider the new model, but we are not so biased towards the new model to keep moving in a smaller distance from the previous value. With that, we can ensure convergence of the algorithm. So we've been talking about we have already started talking about communication efficient distributed machine learning, because when we, as we explained, when we minimize the number of times we communicate with the parameter server, in fact, even before that, when we allow workers to only share their gradients or their models through federated learning, we went one step towards communication efficient distributed machine learning. So the workers do not share their data. So that was the first thing. By minimizing the number of variables per iteration, or by performing federated learning, we have already went one step in developing communication efficient distributed machine learning. However, that can also be improved further. For example, by minimizing the number of workers that transmit per iteration. In fact, even this we have already shown in local SGD or periodic SGD. We are doing that, okay? But we will show later how we are doing that in a way that we consider like the growth of the gradient of every worker, and which worker we allow to transmit, at which one we do not need him, like we do not need to include in the transmission of the current iteration, such that the communication cost is minimized. So that's one way, by introducing temporal sparsity or minimize the number of workers transmit per iteration. Another way, or on top of that, we also could introduce quantization, because when we introduce temporal sparsity, or when we minimize the number of workers that transmit per iteration, so that reduces the number of times a worker communicates with the parameter server, but it doesn't reduce the payload size per channel use. The workers still need to send for example, in full precision communication, 32 bits per element in the vector. Therefore, one possible way to reduce the communication cost per channel use is to introduce quantization, and we will talk about that later. Another way is to decentralize the topology and minimize the number of neighbors that a worker can interact with at any given time. So when we minimize the number of workers that a user can communicate with, we can significantly reduce the communication cost, as we will see later. Moreover, we can also introduce quantization on top of that. So we have spatial sparsity, because when we minimize the number of links or neighbors to communicate with, we actually introduce spatial sparsity. So on top of spatial sparsity, we also can introduce model quantization to minimize the payload size per channel use. Okay, now we come to describe how we make federated learning more communication efficient by introducing temporal sparsity through what is called lazily aggregated gradient descent. So we still consider the same unconstrained optimization problem we described previously, and we already explained like this problem can be solved using aggregated gradient descent, which works as explained in this figure. However, one problem with aggregated gradient descent is that every worker still needs to communicate with the parameter server at every iteration. Even if there is no a large growth in the gradient, every worker has to send its gradient to the parameter server in order for the parameter server to form the system gradient. So with lazily aggregated gradient descent, the paper that proposed this approach said that, in fact, not every worker needs to communicate with the parameter server at every iteration. Therefore, the global parameter at theta k plus 1 is updated using the same gradient descent algorithm, but it uses at iteration k plus 1, it uses like the outdated gradient of all workers, plus the difference between that outdated gradient and the new gradient for only subset of the workers in which the gradient has grown larger than a certain threshold we will describe later. Therefore, at iteration k plus 1, this gradient, it's the updated gradient, is the gradient at iteration k for some of the workers, but not all of them. So this is delta of the gradient. This is the difference between the gradient at k minus 1 and at k for some workers. Okay, for some others, they are still using the outdated gradient. And in fact, this paper showed like that if the gradient, if any worker that satisfied this condition, this condition intuitively means that if the gradient or the difference between the gradient at iteration k plus 1 and iteration k grows larger than a certain threshold, then that worker has to upload its updated gradient, or the difference between the previous and the current gradient. That worker can contribute to the system. The difference that has can contribute to the system gradient, and has more contribution to the decision of the next choice of the global parameter. However, if the worker doesn't satisfy this condition and the gradient doesn't grow as large as being greater than this threshold, that worker doesn't really contribute much, and ignoring that worker will not come at any cost in terms of converging. The algorithm still is going to converge, and in fact, they show it's still going to converge in the same speed as the original one. So in fact, ignoring that worker, which does not contribute that much, it will introduce an error, but that error is very small and it doesn't affect the convergence and the convergence speed of the algorithm. So ignoring that worker will save communication. In fact, will significantly save the communication cost, while it doesn't affect the convergence speed. And according to this algorithm, there are only very few workers who need to upload or transmit their updated parameter at every iteration. So compared to aggregated gradient descent, they both converge at the same speed, but this one can significantly save the communication cost. And in order to look at it from the communication cost perspective, assume that we need to reach accuracy A, therefore we need to run for TA iterations, and at every iteration, the parameter server at every iteration still needs to broadcast the global model to all of the workers. Therefore, there is a communication cost associated with that broadcast, and that's reflected by this parameter here. And then for every worker from n equal 1 to n, for the aggregated gradient descent, every one of them is transmitting. Therefore, this indicator function, which is equal to 1 if the worker is transmitting and 0 otherwise. This will be always 1. Therefore, all of these workers will be always transmitting when we are using aggregated gradient descent. However, when we are using lazily aggregated gradient descent, this indicator function is 1 only if the worker is transmitting and 0 otherwise. And with very few ones, with very few workers transmitting at every iteration, this could be much smaller, and we could save so much in terms of the total communication cost compared to aggregated gradient descent. That's for the temporal sparsity approach. Okay. So the previous approach we explained, it minimizes the number of times that a worker uses the communication link or upload a variable to the parameter server. But in fact, it doesn't really do anything with the number of bits that the worker needs to transmit at every channel use or at every iteration that the worker is transmitting. So in the full precision communication, every worker still needs to send 32 bits for every element in the vector. Okay, therefore that is also still like require a lot of communication overhead. Therefore, to avoid that, quantization on top of lazily aggregated gradient was also proposed. And what we mean by quantization here, every element in the vector is quantized, so less number of bits is transmitted per element. In fact, that number of bits can go as small as 1 or 2 bits. And the algorithm still works the same thing. The global parameter has to update the parameter server has to update the global parameter according to the gradient descent rule. But now this vector, or the aggregated gradient vector, is the aggregated lazily and quantized vectors of all of the contributing workers. So at every iteration, so here theta delta k is equal to the outdated one plus the aggregated difference between the current and the previous gradient. Therefore, if we want to compute the the error in the quantized vector, the error is the difference between the actual one and the quantized version of it. And this is per worker, it's the same thing. Now I described the quantization scheme that was proposed in LAG paper, in the lazily aggregated quantized gradient paper. So the quantization scheme works as follows. At iteration k, the quantization function takes two inputs, the current gradient, the gradient that is computed at theta k, and the previously quantized gradient. So it takes these two inputs and produces a quantized version of the current gradient vector. So the first thing we need to calculate is what we call the quantization range. So for worker M at iteration k, the quantization range is the norm infinity in the difference between these two vectors. Norm infinity means the element with the maximum the largest element in the vector. Okay, so so therefore the quantization range is defined by the element that has grown the largest. So I have these two vectors, the current gradient and the previous one. So I take the difference between in every element, and the element that grows the largest defines the quantization range. And then we center the quantization range around the previously quantized element. Therefore, we have RMK to the right and RMK to the left. So in total, our line with it is 2 RMK. So then how many quantization levels we have is defined by the quantizer resolution, or the number of bits that we need to give to every element. So if that is equal to b, then the number of quantization levels is equal to 2 to the power b minus 1. Okay, so once we have the quantization level, we can find the number of quantization levels and the quantization range. We can find even the size of every step, which is equal to 2 tau times RMK, where tau is defined by this equation. So then we just do the quantization. So we take the difference, we add RMK to produce a positive value. Okay, divide by the step size, and okay, we add half and floor. So because we add half, so we always floor. So that will produce an integer number. Okay, that represents the index of the quantization level. Once we get that, then the difference, or the quantized difference between the current and the previous the current vector and the previously quantized vector is just equal to this term here we have. So so 2 tau times r times q, which computed according to this equation, minus r. So because here we added r to always produce a positive value, but then we need to deduct this r. So for example, take like one choice of q when q is equal to 2b to the power b minus 1, the last quantization level. If it's equal to that, then this 2 to the power b minus 1 will go with the tau, because tau is 1 over 2 to the power b minus 1. Then we will have 2r minus r, which is equal to r, which is exactly this point, because that is the element that has grown the largest, and the difference between the current and the previous value is equal to the quantization level, to the quantization range, which is defined by RMK. So then, so this is defined. This defines the difference, or the quantized difference in between the current and the previous gradient. But what the worker needs to transmit, it needs to transmit the quantization range. And the quantization range, we have to transmit in using 32 bits for precision, but we are transmitting only this element in a full precision using 32 bits. But these elements, because this is a vector, now for every element, we have the index of the quantization level. So we don't send the exact element. We don't use 32 bits to send that number, that real number. We are sending just the index, because once we send RM and all of the workers share the same B, so tau is known at every worker. So for example, here we assume like B is equal to 3 bits. So every worker knows that, or the parameter server knows that P is equal to 3 bits. So the worker needs to send 32 bits to convey this RMK, and needs to send only 3 bits for every element in this vector. So compare that to full precision communication. We need to send 32 bits for each element in this in the gradient vector. But now here we are only sending 3 bits for every element. Therefore, if the model size is large, we see big difference. So we are sending 3 bits per element versus 32 bits per element. So therefore, when we apply this quantization scheme, in total we are sending 32 bits to convey this RMK, plus B bits for every element in the vector, in the quantized in this vector. Okay, so we are sending 32 plus B times P bits. However, in the full precision, we are sending 32 times B bits times P. So when the model size is large, we can clearly see that this approach significantly reduced the communication cost in terms of the number of bits that a worker is transmitting at every iteration. Okay, now we come to describe how we formulate the federated or the distributed machine learning as a constraint optimization problem. But before I go into the details of how to formulate the federated learning as a constraint optimization problem, I would like to briefly go through the key steps of solving a constraint optimization problem. I would like also to mention that this course is not about optimization. So I will just briefly describe the key steps, but I would assume most or all of you have already taken some optimization courses. If not, I will highly recommend that you take optimization courses if you want to do research in machine learning, because optimization is a key tool in doing research in machine learning. So, what we mean by constraint optimization problem, one example is the function we have here, where we want to minimize sum of number of functions. Every function is owned by a worker or an agent, and subject to some set of constraints. Here we assume linear set of constraints. So if every function here is convex, the feasible set, or this is convex set, therefore this is a convex optimization problem. One way to solve this problem is to use what is known as dual decomposition. And the first step in dual decomposition is to formulate the Lagrange function, or the Lagrangian, which is, as we can see here. So we have the sum of the objective function, which is the sum of the local functions, plus the dual variable times this quantity, which represents the difference between the left and the right side of this two terms. So this is the Lagrange function, and at every iteration, we have two steps. Okay, this is another way to rewrite it, but after inserting this inside the sum. So this function can be at every iteration will be optimized by every one of the agents or the workers. So there are two steps. The first step is updating the primal variables. At every iteration, every worker or agent wants to minimize this function with respect to its local variable. And since the other functions, the functions that are owned by other workers, are not functions of this variable, then this guy doesn't need any information from the other agents. The only thing that is needed is the dual variable at iteration k, which can be downloaded from a parameter server to every worker. Once every worker receives the dual variable, then it can solve this problem and update its own primal variable. So, for example, if I of xi is differentiable and have a closed form, then the update of the ith primal variable or ith model, if we're talking about machine learning, is just solving. It's just taking the derivative of this function and equating to 0, which yields a closed form update or closed form expression for the ith model. So as I said, when we take the derivative with respect to xi, all other functions are not functions of xi, so that will go to 0. Then we will end up updating the ith, the primal variable of the ith agent without requiring any information from other workers. We just require the dual variable at iteration k, at the previous update of the dual variable. So after updating the primal variable at every worker, so all the workers will perform that in parallel. So they all update the dual, the primal variables, then they all upload their primal variables to the parameter server, and the parameter server will update the dual variable. Okay, so the dual variable, the step of updating the dual variable is a global step. It's performed at the parameter server. So then y at iteration k plus 1 is equal to y at iteration k plus the step size at iteration k times this what we call the primal residual. So we know this at the convergence point should go to 0 because this constraint has to be satisfied. This is the feasible set. Any xi that satisfies this condition is in the feasible set. And among all points in the feasible set, we are looking for the one that minimizes the objective function. So that will be our optimal solution if every function is convex. So that's the point we are looking for. Therefore, at the convergence point, this will go to 0, and we will have convergence in the dual variable. And in case of strong duality, when this reaches the optimal solution, the primal solution also reaches its optimal value, and we solved the problem. There is one problem with this method, which is called a dual ascent. So that problem is that when for example, assume if is an affine function with respect to one of the elements. So let's say f is a function of a vector that has two elements, x1 and x2. Let's assume f is equal to x1 square plus x2. So now it's a affine function with respect to x2. Now, when we come to updating this, when we come to the step of updating the primal variable, if we take the derivative to 0, then the derivative is not function of x2 anymore. Or in other words, the optimal solution is at that step is minus infinity, which means that the function is unbounded from below. Therefore, though this method is simple and introduce this parallelism in the update, in fact, in reality, it may not be practical to use in many cases. So therefore, there are some other alternatives that we will discuss after this. So here's one alternative solution, which is called alternating direction method of multipliers, or we use ADMM to always refer to this algorithm. So briefly, ADMM initially was proposed to solve this optimization problem, where we have sum of two variables, sum of two functions. Every one, these are two separable functions. Every one is a function of a separate variable, but there is a set of linear constraints that relate these variables to each other. So the way we solve this problem using ADMM is by formulating what we call the augmented Lagrangian. So it's the same as the Lagrangian up to here, up to this point. So we have the objective function plus the dual variable times this term, but we add this quadratic term here. Okay, this quadratic term at the convergence point, this will go to 0, and the solution of this is exactly so the same as that. So at the convergence point, it still ensure convergence to the optimal solution in case of convex functions. So its function, as we see here, L rho, it's function of rho. So the choice of rho can affect the convergence speed of the algorithm. So therefore, the only thing that we add here is this quantity. Now adding this a quadratic quantity, now we don't have that issue. So for example, if x, like if it's affine in one of the variable, when we take the derivative, okay, with respect to that, okay, this is not the derivative of the function itself is not function of that of that element, for example, but that element still appears here, and we still can update each variable in a closed form expression. But of course, that comes in at another, it comes at a cost. Now, if we look back to this problem, all the workers can update their models in parallel, because there's no term that combine these variables with each other. But now, after introducing this term, now here, every worker, workers cannot update in parallel, because when updating for X, I need to use Z, okay? Therefore, the way the standard ADMM, or what is called as Gauss-Seidel ADMM, updates is as follows. The first variable is the primal variable. The first primal variable is updated using the kth version of the other variable and the kth version of the dual variable. So we update the first variable. So there is a sequential update here. The first primal variable is updated. Then at the update of the second primal variable, we use the new version of the first primal variable, the previous version of the dual variable, and we minimize this augmented Lagrangian with respect to Z. So to find ZK plus 1. So we first solve this to find X. Then given the new X, we solve this problem. Given the new X and the previous dual variable, we solve this problem with respect to the second primal variable. And after we update the two primal variables, then we update the dual variable according to this equation. So the step of updating the dual variable is similar to the dual decomposition one. That is the standard version of ADMM. However, ADMM was extended to some of more than 2 functions, and a few variants of ADMM were proposed. This is the one we just described, the Gauss-Seidel. However, there is another version of ADMM called Jacobian ADMM. In Jacobian ADMM, in fact, what happens is that we allow the workers to update their models in parallel. Okay, we don't do this alternation. So though we have this term here, but everyone is going to use the previous version of the other one to update its variable at the current iteration. So X and Z will update in parallel. X will use the K plus 1 version, the kth version of Z, of the variable Z, and also Z will use the kth version of the variable X. So this is what is described here. So under some conditions on the matrix, if all these matrices, AI for all I, the algorithm still can converge, okay? However, those conditions may not be practically maybe difficult to satisfy. Therefore, proximal Jacobian ADMM was proposed, and the difference between proximal Jacobian and Jacobian is just the proximal theorem we have here. So we have the same thing, the same problem, the same thing. Everyone will minimize. This is just another way to write these two terms together. Okay, so it's the same thing. So this plus the proximal theorem. The proximal theorem is added here to to not let the update grow so large at any given iteration. So we let every variable, we let every worker or agent update its own variable using the kth version of all of the other agents, but at the same time we don't let the update to grow so large. So we introduced this term that is like minimize, like we want the new update to be close to the previous one. With that, with some conditions on this, the choice of this norm, this algorithm is shown to converge eventually. I would like to say, though I'm now talking about distributed setting and saying every agent wants to receive xj for all j doesn't equal to I, but that is that actually comes at very very high communication cost, because you want to receive the variable from every other worker in the network, okay, in order to update yours. So therefore, in fact, these versions of ADMM are proposed not for the distributed setting, but for solving the optimization problem, this optimization problem in a single machine, okay, where exchanging these variables doesn't come at a communication cost. So all these variants of ADMM that I just described did not consider this distributed system and communication with between agents. Yeah, so we will come later to the, in fact, here now. Here we describe we formulate the federated learning as a constraint optimization problem. So now we don't say if n of global theta, we say sum of fn theta n such that every theta n is equal to a global variable. Now with this, so we formulate the augmented Lagrangian and then the primal variables, because now every primal variable is just has a constraint with the global variable only. So therefore, every worker needs at iteration k plus 1 to receive the kth iteration of the global model in order to update its local problem. Therefore, all of the workers can still update their local variables in parallel, since they all, because it's alternating, it's still alternating, but it's alternating between updating the local variables of all workers in parallel and the global variable. So at one iteration, all of the workers update their variables, their local variables in parallel, and then after that, the parameter server will update the global variable, the one that satisfy the one that minimizes the augmented Lagrangian, which turns to be the average model, of course, including some. It's still function also of the dual variables of all workers. But after that, the dual variables of all workers are updated in parallel. Each worker will update its own dual variable. The dual variables doesn't need to be communicated between the workers and the global model, because at iteration k plus 1, both the parameter server and the workers have the k plus 1 version of the global model and the local models. So if the workers as well as the parameter server can update the dual variables locally without exchanging any more information. So by formulating so briefly to summarize, so when we use ADMM to solve the federated learning problem, this is the way we formulate the problem. Then we come up with the augmented Lagrangian, and then since the augmented Lagrange, since every one of these workers have a joint constraint with only the global parameter, which is owned by parameter server, then at every iteration, all the primal variables of all workers are updated in parallel by minimizing the augmented Lagrangian with respect to the local model. Therefore, they all update their models in parallel. After that, they all upload their models to the parameter server, and the parameter server can upload the global model, the one that minimizes this augmented Lagrangian or takes the derivative to 0, which turns out to be this one. And then after that, the workers and the global parameter can update the dual variables without any more communication for the iteration, for the same iteration. And again, the step of updating the dual variable is shown here. Is just lambda k plus 1 is equal to lambda k plus rho times this primal residual. Eventually, this will go to 0. We will have convergence in the dual variables and in the primal variables and in the objective if we have a strong duality. What I mean by strong duality, that the maximum of the dual problem and the minimum of the primal problem are this, meet at the same point. So this is the communication cost to reach accuracy A. we have one broadcast if per iteration. To reach accuracy A, we need to go for TA iterations, where we have the cost of using the downlink at every iteration, plus the cost of using the uplink from every worker to the parameter server. So we have n workers, we sum up all of these. This is the total communication cost. Now we come to describe building a training machine learning model using TensorFlow. I will walk you through all the steps from building just one layer, one neural network layer in a single machine, and then we will go deeper, build a deep neural network in a single machine, and then after that we will implement the distributed or the federated version of it, where we have a number of collaborating workers or agents that are training collaboratively. So in short words, TensorFlow is an open source library that helps you develop and train machine learning models. It's based on Python. And as I just explained, our task is to build and train a deep neural network model to perform image classification. We will start with a simple model that runs in a single machine, and then we will extend it to distributed or federated learning setting. I would like to mention that the model for the single machine based model, I'm using slides from this tutorial. Okay, it's a long tutorial that walks you through all the steps, but for single machine. So for detailed steps, you can watch this video. It's available on YouTube. So our task is to do image classification, and we will use this very famous data set. Its name is MNIST data set. It contains 60,000 training images and 10,000 testing images. These images are for handwritten digits, as you can see here, the digits from 0 to 9. So for every one of them, this 0 has been written in different ways, one the same thing, and so on. Every image is 28 by 28 pixels. So we will treat every digit, we will take every image, and we have the image itself, as you see here in the figure to the right. We have the image and we have the label. So for the training set, we will have the image and the label. We will use them to train our model, and then we will validate or test our model on the 10,000 testing images, where we have the images, but we need to infer the label. Okay, so as I just mentioned earlier, we will start with the simple one layer neural network. So since we have 10 images, the minimum number of layers we can have, the minimum number of neurons we can have is 10 neurons. So we will have one layer, 10 neurons. Every neuron does a simple task. It just takes a weighted sum from all the pixels. So what we do first, we flatten all the pixels, okay, to have one vector. Later, when we do convolutional neural networks, we're not gonna flatten the image, because by flattening the image, we are destroying the shape. So, but now I'm just starting with the simple approach, where we just use deep neural network. We do not use convolutional neural networks for now. So then we need to flatten the image, so we will have one vector. So we used to have image that is 28 times 28 pixels. It will become only one vector of size 784 pixels. Then every neuron does a very simple task. It takes a weighted sum from all inputs. It adds a bias, and then will feed the input through a nonlinear activation function. But now for the one layer classification, so the output of the neurons will go through what we call softmaxing function. Softmaxing function is an exponential normalized function. So when we take the output vector, okay, and we take exponential, we take like the exponent to that vector, then what we are doing, we are increasing the difference between the elements in that vector. And after we normalize that vector, we will produce numbers between 0 and 1, and hopefully like one of them will be very high and the others are very small. Ideally, one of them will be 1 and the others are zeros. So think of it like lamps. One of them will light up, telling us what number we have entered. So for example, if you look into this image, we are passing 8. Ideally, only like the 80 neuron would be 1 and others would be 0. So with that we have already like figured out the correct label of this image. So that's one neuron, that's one layer neural network. So softmaxing is a function that produces an output vector. The elements of that vector can be interpreted as probabilities. So the first element is the probability of the image being 0. The second element is the probability of the image being 1, and so on. So we feed a patch of images. For example, here we show like an example where we feed where the patch size is 100. We feed patch of images. Then, as I explained it, we will have like for every image we pass, we have weighted sums of all the pixels plus the biases, and then we feed this quantity through the softmaxing to produce one vector per image. So when we feed 100 images, then we will have 100 labels or 100 vectors. Every one of them is of size 10. Only one, ideally, only one element is 1 and the other 9 are zeros, reflecting the label of the image. And this is what is called one hot encoded. So where like the label is 10 is a number of like, for example, in our case here, it's 10 elements and only one of them is 1 ideally and the others are zeros. So therefore, this is the like how this like softmaxing is implemented on a patch of images. One thing here to mention, because this now x times w will produce 100 times 10 and we have only 10 biases, but in in Python it's very simply to like repeat those 10 elements in the bias to ensure that this you don't get an error. So when you do it in Python, it happens internally. So when you add those two quantities that are not two matrices or that are not in the same size, then one of them will the elements will be repeated to fill the matrix. So the sum will take place without giving any errors. So in TensorFlow, we just need to write this line. That's it. It's a very simple command. You write this line. You already defined the matrix of the weights, the biases. You have the input images, batch of images. Then you just need to say to write that y is equal to this, and then so where here you do multiplication, addition, and then you do softmaxing. Then you get the output label y. Okay, now we come to describe the training process itself. So how do we train? How do we find the set of weights and biases such that an objective function or a loss function is minimized? So the loss function represents a certain distance between, some kind of distance between the actual label as it's shown here. So for example, if my image is 6, then for the training, I know that this image, because I'm feeding this image, so I have 1 in this position, in the 6th position, and 0 everywhere else. So the image is encoded into the label of the image is encoded into this vector, and then the output of my neural network would be some vector with some values here. And in order to train my network to figure out the right label, I need, as I said, to minimize some kind of distance between this vector and the output of the neural network. There are different ways to measure, like different, I would say, loss functions can be chosen. For example, Euclidean distance still can work, but cross entropy is shown to perform better. So the cross entropy is just like you take like every element here times the log of the corresponding element of this vector, and then we sum all of them and we take the negative of that, because the log of those values that are less than 1 is always negative. So that's our loss function that we want to minimize. Therefore, we want to train the network using this loss function, and then eventually we converge to the set of weights, because when we are training, what we are doing, we are finding the set of the weights and biases of our neural network such that this objective function or this loss function is minimized. So this loss function, when it's minimized, means that we are classifying images at higher accuracy. Now we come to how we define different parameters in using TensorFlow. So we input images in batches. Therefore, we define X as the input batch of images. We define it as a placeholder. At every time we feed a batch of images. That's why we use none here. So this would become the batch size. So therefore, X is defined as a placeholder. So we feed images. Every image is in size of 28 times 28 pixels. We define the weights and the biases as variables. The weights, since we flatten the image into 784 in a vector of size 784, and we have 10 neurons, then the size of this matrix would be this. Since we have, for the biases, since we have only 10 neurons, then we have only 10 biases. So it's a vector of size 10. So so defining the variables as simple as we see in this slide. So this is reflecting the input batch of images, and these are our variables, the weights and the biases. So here, how we compute the output. So as I said, we are flattening the images. So we reshape the size of X, because X here is 28 times 28. We reshape it. It's a matrix. We reshape it in a vector. Then we just like, we do X. We multiply by the weights and add the biases to have Y at the output. This is the predicted label. And then for the actual label, we have another variable that's a placeholder that contains the actual label of every image in this batch, in the input batch. And the label is a vector of size 10, as we explained it. It's one hot encoded. In that vector, only one element is 1, its position, reflecting the actual label of the input image. So here we just, this line just to define our objective function or our loss function, the cross entropy that I explained in the previous slide. Here, these two lines are just to compute the accuracy. So we are accurate in estimating and predicting the label when the max of the vector Y, the maximum value of and the vector Y matches the maximum value in the correct or the correct label or the ground truth vector. So that's, these two lines are about computing the accuracy. And now we come to the optimization part. So we are running gradient descent. So this is the way you choose the optimization algorithm. So we are running gradient descent algorithm, and this is the learning rate or the step size. I have already explained gradient descent algorithm and how it works. So we start with the initial guess, and then we compute the gradient there. And since the gradient is a vector that points towards the maximum, we will keep moving towards in the negative direction and of the gradient. Eventually, we will reach the bottom point. So then every training step is just running this optimizer on this cross entropy function, passing this as the loss function. Now we describe how to perform a training session using TensorFlow. We define a number of iterations. At every iteration, we feed a patch of images with their corresponding labels. In this case, the batch size is equal to 100, so we feed 100 images with their corresponding labels. This batch of images is randomly selected from the training data, and then we perform one iteration in our optimization algorithm, which is in this case gradient descent, and we can compute the accuracy at every iteration on the training data. And as well as the accuracy on the testing data. We can perform that per iteration, or like every couple iterations we test after we train for some time. We measure the accuracy of our model using the testing data. And what matters actually is the accuracy in the testing data, not the training data, because the testing data was not used to train the model. So this is the main loop to train the model. So now here we can have a look in the code, the whole code. So here we define the parameters. Here we just show how we define how we compute the predicted label using our neural network, our simple one-layer neural network model. And here is the actual label. So it's defined as a placeholder. Here we define our loss function. Here we define how we compute the accuracy. Here is our optimization algorithm. And here is the main loop to train. That's the whole code together. So one layer neural network may not lead to the best accuracy that we can achieve. Therefore, in order to improve our accuracy and achieve better accuracy, we may consider going deeper. So we have more layers. So we have the first layer, which is exposed to the input image. And we have a number of hidden layers and then the output layer. So in such a structure, the neurons at the input layer and the hidden layers, every one of them has to take weighted sum from all inputs. So the first layer, every neuron will take weighted sum from all pixels, and the ones that comes in at the next layer, every one of them will take a weighted sum from outputs from the outputs of all neurons in the layer before that one. So then after taking a weighted sum of that and adding the pi's, every neuron will feed the output through an activation function. Of course, it shouldn't be the soft maxing function. Soft maxing is just for the output layer, for the last layer, to help in doing the classification. So in the for the neurons in the hidden at the input layer, there used to be a number of activation functions proposed in the literature. I think these are like the sigmoid and ReLO are the most widely used ones. It was shown that ReLO function, the function that is shown here, which is just 0, it's equal to 0 below 0, and it's just linear between 0 and 1. So ReLO function was shown to perform slightly better. So it has, especially for the image classification problem, so it has been used. And this is the simple, like how to write it in TensorFlow. So for a neuron, the output of that neuron is just weighted sum of the input, and then you feed through ReLO function. This is how to write it in the TensorFlow. So here we describe how we go deeper and construct or build a deep neural network using TensorFlow. So here in this example, we have a neural network that consists of 5 layers, 1 input layer, 1 output layer, and 3 hidden layers. So these are the number of neurons at every layer. So at the input layer, we have 200 neurons. At the second one, we have 100 neurons, and so on. So one thing to mention, at the last layer, the output layer, we should have 10 neurons because we are classifying 10 classes. So then this is the way we define the weights and the biases of every layer in TensorFlow. So W1 and B1 are defined here, as we can see. Both are variables. So since the first layer is exposed to the input image, therefore the W1 is defined as a matrix of this size. This is the number of pixels times the number of neurons in that layer. So here we just like choose some. This is like some distribution. We initialize the weights according to this distribution, truncated normal, with this choice of standard deviation. Just to avoid like initializing with zeros, we can have like better results or faster accuracy, faster convergence when we initialize using truncated normal. Yeah, that's for the weights, for the weight matrix of the first layer. For the bias vector, it's of size k. The number of elements in the biases vector is always equal to the number of neurons, because we have one at that layer, because we have one bias per neuron. So that's for the first layer. For the second layer, so since the output of the first layer will be the input to the second layer, therefore the size of W2 will be of, it will be a matrix of size K times L, where K is the number of neurons in the first layer, and L is the number of neurons in the second layer. So for every layer, the weights will be a matrix where the number of rows is the number of neurons in the previous layer, and the number of columns is the number of neurons in that layer. And as I mentioned, for the bias, it's always of size, the number of elements is always equal to the number of neurons in that layer. So this is how we define W2 and B2. The same thing for WB3 and B3 and so on. For as I mentioned, for W5 and B5, since it's the output layer and we have 10 classes, therefore this has to be 10. Okay, it has to be like equal to the number of classes. So then we feed the images as we used to do for the one layer network. And here, as I mentioned, the output of every layer is going to be the input to the next layer. So for the first layer, since it's exposed to the input data, then Y1, the output of the first layer, will be the X, where X is the input data, XW1 plus B1. Then we perform sigmoid. Yeah, as I said, we could do sigmoid or Rela activation function. Here in this specific example, we use sigmoid for the first layer and all of the hidden layers, but we use softmax for the last layer. So as I said here, the output of the first layer Y1 will be the input to the second layer. So now when we go deeper, the way we truncate those layers is as follows. The output of the first layer is input to the second layer. The output of the second layer is input to the third layer, and so on. So that's how we construct, or how we build a deep neural network. So then we perform soft maxing in the output of the last layer to find the predicted label. Okay, to achieve better accuracy, we use convolutional neural networks, and the reason behind that is that we have one issue with the simple approach that I described earlier, and that issue is that we are flattening the image before we feeding it through the neural network, and by flattening the image, we are destroying the shape. So we're not using shape related information. So, for example, the pixels that are nearby each other, they have correlated information. So there is correlation. So by flattening the image, we are not really benefiting from such correlated information. Therefore, a convolutional neural network is shown to perform better in terms of the accuracy when it comes to image classification. So at high level, so what we have for every layer, we will define the weight, the weights as shown here. So we have the filter size. So how many pixels, how many pixels, like how much, like what's the width and the window size of the filter. So here 4 by 4, 4 pixels by 4 pixels, and we have the number of input channels. So here, for example, in this colored image, we have 3 input channels and we have 2 output channels. So we use 2 sets of weights. So we filter with one. So every pixel, every neuron will take weighted pixels from the window above it. Okay, and then we move from one to the other using the stride. So if we are moving 1 pixel at a time, then stride is equal to 1. And then we with the first set of weights, so every neuron will use the same set of weights. With the first set of weights, we will produce the first output channel. With the second set of weights, we produce the second set of the second channel. So that's what we mean by 2 output channels. So 2 different choices of the weights. Okay, so that is at high level how we do this convolution per layer. So then if I have multiple convolutional layers, then we will go one after the other. The same thing, the output of one layer is the input to the next one, and so on. Eventually, we have to have fully connected layers. So we reach a point where there is the first fully connected layer. We may run into a number of fully connected layers before the last classification layer. So this is how we do it in TensorFlow. It's very similar to what I described for the basic approach. So here we define like W1, we define what I just explained. So the structure of the so here the filter size and the input channels and the output channels, and after a number of convolutional layers, then we will have the fully connected layers, which are defined the same way we explained in the basic approach. The last layer, since we are still solving the same problem, classifying handwritten digits, and we have 10 classes, then the last layer here we should have this has to be 10, and that's for the last layer. So then here how we compute the output after each layer. So it's very similar here for the convolutional layer. Convolutional layers, we use conv2d because we are doing 2D convolution. So then we we have 3 convolutional layers, and after the output of the last convolutional layer, we flatten the output. Then we have this as an input to the first layer in the set of fully connected layers, and the rest is the same as we described earlier. So the last one will be the softmaxing here. And for example, in this specific example, we have 3 convolutional layers and 2 fully connected layers. The last one is the output layer. So with that, I explained like how we do it in a single machine, how we do image classification using TensorFlow in a single machine. Now I will come how to do it using distributed system. So I'm here just reminding you of the setting of the distributed system. We have a parameter server and we have a number of workers. And what we are going to implement is just like the distributed stochastic gradient descent, or the mini batch, the distributed mini batch gradient descent algorithm that I explained earlier. So we are going to implement this using TensorFlow. Okay, now I describe and run this code which implements federated learning. We are using distributed mini batch SGD, where at every iteration, every one of the workers will compute its own gradient with respect to a global model that is downloaded from the parameter server. It will compute the gradient using a randomly selected mini patch, and then it will share the gradient with the parameter server. After the parameter server aggregate all the gradients of all workers, it will perform one global SGD iteration. So I'm using a Jupyter notebook. So as you can see here, I can run one cell at a time by clicking Shift and Enter. So the first cell, we are just importing some important libraries. So here we are just loading the data set in the second cell. So here we are defining the number of classes, and the number of classes is equal to 10 here because we have 10 classes. We are classifying handwritten digits from 0 to 9. So there are 10 classes. We have 20 workers or 20 agents. So we run this cell. This is about like preparing the data set. So we're not using the whole data set here. We are using for the training and the testing data, we are using subset of the data set. So here is the important cell. So we define every worker as we define a worker as a class, and then for every worker we have the set of weights and the gradients. So here we assume that every worker have a neural network that consists of 3 layers. So therefore we have the weights and the gradients with respect to the weights of every layer. This function to build the neural network of a specific worker. This function, we use it later in the main loop to randomly select a mini patch at every iteration. This is just, this cell is just to define the loss function. So we use cross entropy here to compute just to compute the accuracy. Here is the function that computes the gradients. So here we compute the gradients by calling this function. So we compute the gradients with respect to the trainable variables, and the trainable variables here are the weights. So we don't have biases here. The biases are zeros. So we define the trainable variables, and then we compute the gradients with respect to them. And this function computes the grades and also computes the loss at the given at this given model or this given set of weights. So we run this cell. Here we are we are defining the central model, and we are like creating the users. So we have now already created the users and defined we're not using this row here, I think, the row and eta. So let me just, okay, so we created users. We defined the central model. This function to split the data set across the users. So they have disjoint data sets for the training and for the testing. No, for the testing is the same data set. For the training, we have the whole training data set, and we distribute it across the workers. Now here we define the mini batch size. So every iteration, every worker will use a mini batch of size 100 samples. The number of iterations and local learning, the learning rate or the step size. So we're not using this number of local iterations in this code. So now here is the main loop. So we start by downloading the central model. So the weights, the model of every user will be equal to the central model, and then we will enter this loop. So we compute the gradients with respect to the current model. This is just assigning the gradients to this to their variables. So then we have the gradient with respect to the weights of the first layer, the second, and the third layer. After we compute the gradients, these gradients will be uploaded to the parameter server. The parameter server will perform one SGD step. So here we are doing it per layer. So we aggregate the gradients of all users for that specific layer, and then so for every layer we perform SGD step. And then after that, the central model will be downloaded to all of the workers, and things will repeat again. This is just to compute the accuracy at every iteration. So then after all users download the central model or the global model, then we go again here. I forgot to mention this first part. This is like to select, to randomly select a mini batch for every worker. So because when we are computing the gradients, so every worker has to select a mini batch and then compute the gradients. So this is the main loop. Every worker will select a mini batch, compute the gradient, then all the gradients will be uploaded to the central, to the parameter server. The parameter server will perform one SGD step, and then will the new global model after performing the SGD step will be downloaded to all of the workers. Then each worker will update its own local model, which is equal to the central model. And then again, it's gonna repeat again. So we'll go to the next iteration, pick a new mini patch and compute the gradient and so on. So now if I run this loop here, now it's gonna here. As you can see, the numbers are increasing for both the testing and the training accuracy. Now here around 20s, around 30s, around 40s, 50s. So as we train more, the accuracy is improving for the testing and for the training. So after this finishes, then we can print out the last accuracy we got, and we also can plot the testing and the training accuracy, as we can see here using this function. So with that, I end this part of the course, and I have a homework for you. I will ask you to implement, instead of mini batch SGD, you will be implementing local SGD, which I described in the lecture itself. Now we come to the last slide in lecture 1 in the third part of the course. I'll be giving you a homework to do. I have already explained it and walked you through the steps of implementing federated learning using mini batch SGD. So I will share the code with you, and you will start from that code, and you want to modify it to perform federated averaging using local SGD. I have already explained the steps of local SGD in the lecture, and here I'm also re-highlighting the key steps in federated averaging using local SGD. So the key steps, as you can see here, the parameter server will start with a global model, and we'll share it with all of the workers. Each worker will start from that global model. It's gonna take it as initializer, and it will perform a number of local SGD iterations. So it will move away from that global model. So it will perform a number of local SGD iterations. Then it will produce a new model, and then each worker will share that model with the parameter server. Then the parameter server will average the models of all workers to come up with a new global model to share it with the workers for the next iteration, and so on. So you need to implement this. You will start with the code that I will provide, the code that does mini batch SGD, and your job is to do this local SGD algorithm. We'll email to you how you submit this homework, what should be the way you submit the homework. Maybe I will ask everyone to maybe record from its like a screen, or send the code, or maybe I will meet you and ask some questions and ask you to run the code. We'll discuss, we'll see how to do that later. Thank you so much, and see you in the next lecture.